Hello, this is FlippedHarber for Precalculus. In this video, we're going to cover Section 4.2, Exponential Functions. Our objectives for this lesson are to evaluate exponential functions, graph exponential functions, and define the number e. The outline for this video will start by talking about something you should be well aware of, the laws of exponents. We'll look at what an exponential function is. We'll talk about the base e. We'll talk about graphing exponential functions. We'll talk about transformations in graphs, and then we'll look at an example. Now, these 6 laws of exponents you should be well aware of. If you multiply exponents, that is, when you multiply two numbers that have exponents and have the same base, whether that base is a number or a variable, you can just simply add the exponents. A power to a power means that you multiply the exponents. You can distribute an exponent in as long as you have a number and a letter, or two numbers or two letters multiplied. You can't distribute a power like this if they're added. You should know that 1 to any power is 1. You should also know that a negative power basically puts the term down to the bottom of a fraction, and anything with a 0 power is equal to 1. Now, an exponential function is simply a function where the variable is an exponent on a number that is greater than 1 and not equal to 0. We don't really talk about the exponent being on a negative number because we can always just look at that as a transformation. So we like to start with exponential functions as an exponent on a positive number. Now, that number should not be equal to 1 because 1 to any power is just 1. So f of x equals 1 to the x is actually pretty boring. Now, this is probably a good time to talk about e. Now, e is approximately equal to 2.718281827. Now, it goes on from there. It's an irrational number with no repeats. It's a lot like pi. It's a number that just kept on showing up as people were discovering math, and we just decided to name it because it was showing up on its own so often. You could think of it kind of like, that stray number that somebody made the mistake of feeding and wouldn't just go away. So you got to put a tag on it and call it your own. Now, the formal way of defining e is with this limit where n is going to infinity. Now, if you're not exactly sure what the limit means, just take this expression and plug a big old huge stinky number in, and you're approximately going to get what e is. Now, the reasons we need to talk about e is a really common base for exponential function. That's probably why they chose e, exponential. It just shows up so often in exponential work and the inverse of exponentials, what we refer to as logarithms, that we just have to introduce it now so that we can talk about it. Alright, so let's talk about graphing exponential functions. Now, here we see two very similar exponential functions, 2 to the x and 1 over 2 to the x. So these two are inverses, so that's why I show them together. But I wanted to point out some common aspects of all of these exponential functions. First of all, the domain is all real numbers. We can plug positive numbers in for x, we can plug negative numbers in for x, we can even plug 0 in for x. Our range is all y such that they're greater than or equal to 0. Now, that means that we can get out only positive numbers. Now, obviously we can change that with transformations, but as long as we haven't transformed it, as long as it's a positive number with our variable exponent, we can only get out positive numbers. Now, it goes through the point 0, 1. That means that the y-intercept for an untransformed exponential function is 1. Now, that's true whether it's a base 2, a base 3, a base 0.5 like we see here, or whatever base, even a base e. They all go through the point 0, 1. We have a horizontal asymptote at y equals 0. Again, an asymptote is a line that the graph forever approaches but never crosses or touches. And we can apply all the transformations that we've talked about before to these exponential functions. The quote-unquote inside is in the power. So whenever you talk about the inside changes, those are the horizontal changes to the graphs, those are up there in the power with x. Now, while we're talking about transformations, only a shift up or down will move that horizontal asymptote. If we horizontally stretch or compress it, that just stretches or compresses the horizontal asymptote. It doesn't move it anywhere. If we flip it over the y-axis, well, we still have the same horizontal asymptote. Even if we flip it over the x-axis, we still have the same horizontal asymptote. It's just approaching it from the bottom. Only a shift up or down will move that horizontal asymptote. So let's talk about transformations in graphs. Here we see the graph for the function f of x equals e to the x. That nice exponential function. What I want to do is talk about transformations and get the graph of f of x equals 7 minus 3 e to the negative 2x. So a lot of changes. There's actually 3 changes, or actually 5 changes if you want to talk about it, to this function in order to get our new function. So let's talk about them one by one. First of all, let's talk about the inside change. That negative 2 means that the graph has been flipped over the y-axis. That's a horizontal change. It's an inside change. And it's been horizontally compressed by 1/2. Remember, changes inside always do the opposite of what we would expect. We would expect that multiplying by 2 would stretch it out, but it actually compresses it by 1/2. It's going to make it look really skinny. The asymptote is still at y equals 0. The y-intercept is still at 1. That horizontal change has not moved the asymptote, and it has not moved the y-intercept. Now let's move out a little bit and talk about that minus 3 that's in front of the e. It means that it's flipped over the x-axis, so now it's pointing down instead of up, and it's been vertically stretched by 3. Now the asymptote is still at y equals 0, but the y-intercept has been moved to negative 1 and then stretched down to a negative 3. Our last change, that 7, that's going to move the graph and the asymptote up. So the asymptote now is at y equals 7. The y-intercept is now at 4. Now, we see what the original graph was, and here we see the new transformed graph. That horizontal asymptote is now all the way up there at y equals 7. The y-intercept is now at 4. This graph is technically taller and skinnier. It's kind of hard to distinguish. Is it tall or is it skinny? It's both. And we see all those transformations applied. Alright, so we're going to end with an example here. I love problems like this because it really makes you stop and think about what really gets done to an exponential function. It says if 5 to the negative x equals 3, what does 5 to the 3x equal? Now, we're going to be able to answer this without actually solving for x. Okay, we'll talk about how to solve for x in the future, but we're going to do this without actually solving for x. What I need to do is think about where I'm at. 5 to the negative x equals 3. And I need to think about where I need to end up. I need to end up with 5 to the 3x. So how do I change that 5, that stuff on the left? And in the process, what's going to happen to that 3, that stuff on the right? So the first thing I need to do, and not that it really matters what order you do this, by the way, first thing I'm going to do is I'm going to get rid of that negative on the x. So the way I accomplish that is actually put it to a negative power. Now that negative 1 power is going to flip the 3 into a fraction. So I get rid of my negative, it turns the other side into a fraction. Now the next thing I need to do, since I got rid of the negative on the x, I need to put a 3 there. So again, I'm going to do the whole power to a power. So I'm going to put the 5x to a power of 3, which means I put the fraction to a power of 3. So that means that 5 to the 3x is equal to 1 over 27. Just a few simple changes, and I've managed to figure out my answer without solving for the variable. Okay, so it's time for you to try some of these on your own. I'll see you in class, and I'll see you online.